All right, so what we're covering now is at times, this is going to get a little complicated because what we're doing is we're adding vectors. We're covering rotation, and we're going to cover how rotations add. Now, angular momentum is a vector, and angular momentum is how you describe rotation. It has all the information of rotation, and it's in a single vector, right? Remember, it's the axial level field. If you have two things rotating on top of each other, like think of a gyroscope, right? You played with gyroscopes as a kid, right? Pull the string. Imagine you had a gyroscope on a gyroscope, right? So the angular momentum vectors would simply add. Right? So there's no problem with that in physics, mechanics. It's really not a big deal. We have a major problem in quantum mechanics in that when you try to do that, the vector is not fully defined because of the uncertainty principle. Oh, God. So you're trying to add two vectors and you're missing components of both vectors. Now, you still have to do this, but how? So that's why this is going to get at times a little bit cross-eyed. But overall, at the end of the lecture, mostly on Wednesday, I'm going to introduce you to a tool called the Clebsch-Gordan coefficient, which is going to make this actually really, really easy. And you can do some really complicated things. Now, term symbols are what I'm going to end up getting you to do, which is, let's see, I think I have an example. One example is like if you have, let's do 2p, x, y, z, and part of term symbols, atomic term symbols, which are very important for transition metals, is to describe what you're seeing here. Now I'm not going to use, you don't want to use px, py, and pz. Do not do that. Use p0, p plus or minus 1, right? The native solutions of the spherical harmonic equation, right? So we covered that. Remember that that's pz and plus or minus is a combination of px and py. It's just done, remember px and py orbitals were invented just to make it easier for undergrads to understand this stuff. Okay, now when you have to write a description of this, what you're going to do is, hopefully you remember this, you have 2s plus 1l and j. So total spin, now here it would be 0 because up cancels down. So this is 1, and let me go ahead and tell you is 1d2. And hopefully you're looking at that thinking, okay, the one part, 2s plus 1 is the 2 part because there's no spin type angular momentum because those cancel. But the L is 1, right? This is a P state. L of 0 is S, L of 1 is P, L of 2 is D. This is an L of 1, it's a P state. So why is the term symbol a D? Well, you'll see. By the way, the hint is notice the M sub L, 1, 2. Yeah, there you go. That's where it's coming from, by the way. So, so this is what I'm going to show you how to do. But really, this is really useful. But really, this is more about understanding the differences between, let's say, carbon-carbon. Okay, let's do a carbon-carbon. Let's do a carbon-carbon bond, right? Okay, so you know all about that, right? But now let me, hopefully you have in your mind just a native picture of what a double bond looks like, right? So it's like I shouldn't really have to say too much. Okay, but now what about this situation? Now how do you describe this? You want to describe it like that. Do you? Or do you want to do it like this? Now you see, what you're doing here is you're going from an understanding of a bond. You know that, and again, that hopefully we don't even need to talk about what it means to have a carbon-carbon bond. But then you got to think of actually a molecular orbital which has 3 of those. And then you got to think of it like, wait a minute, no, it's actually a little bit more complicated than that. It's actually a resonance structure. So what's really happening, by the way, is that your molecular orbital is this resonance structure, but what you understand very well is a double bond. The reason that this happens, that your understanding of a double bond does not equal the true molecular orbital, which is the resonance structure, is because the Hamiltonian doesn't have this double bond as an eigenstate. In other words, it's not a molecular orbital in its own right. You understand it quite well, but the Hamiltonian, complications in the Hamiltonian require the resonance structure to be the actual molecular orbital. So just like you understand what spin up, spin down means in a 2p orbital, this again is very sensible to you. The problem is that the Hamiltonian doesn't care about this description. This description right here, which you've been learning since high school, does not work in the Hamiltonian. The Hamiltonian will not take this wave function, spit out an eigenvalue times the wave function. So this is not in itself a eigenstate. So you have to figure out how the Hamiltonian works with your, to be blunt, sorry to be rude, but your more primitive understanding at this point of electronic structure. So that's kind of the big picture here. Anyway, I'm blowing lots of time. So unfortunately, a lot of the complications of quantum in electronic structure, and again, we're going to stick mostly with atoms, comes down to angular momentum. And so remember, in 3 dimensions, and we always have to be in 3 dimensions, in spin, you know, polyspin matrices, which describe the spin up, spin down of an electron, which is, of course, still active and a big problem for molecules. They still have that same behavior of spin. And also, don't forget that everything we've covered in terms of spin, those polyspin matrices, SX, SY, basis set, all of those rules, all of those matrices and vectors, SX plus is plus, plus, minus, right? All that stuff, all of that was figured out using the Stern-Gerlach experiment, where we simply manipulated the output of Stern-Gerlach machines to build up a set of rules which are Dirac notation correctly, described. It turns out, and I hinted at this, I showed you at one point, towards the end of our discussion of Dirac notation as it applies to Stern-Gerlach, that the rules we had derived were basically identical to the rules of angular momentum. Now, that's going to get really driven home right now. So anyway, this is what you learned about when we did 3D, so particle and sphere. Of course, this is a mini Schrödinger equation for the hydrogen atom. And of course, here is our eigenvalue. Now, this would be the rotational energy from a particle in a sphere. Note that the total wave function is going to be 1 for the L state and 1 for the M state. The combination, of course, is the spherical harmonic. And of course, M is a function of L, and that's just raw mathematics. Mathematics giving you that. And so degeneracies are of course, dictated by the M, by the sub-quantum number, sometimes called the magnetic quantum number, to be, pain about it. One thing I didn't spend a lot of time on is there are rotational operators for, so here, now you've seen this one. This is, of course, the Z type. When you do particle on a sphere in 2D in cylindrical coordinates, right? I think you actually derived this. But you have operators for Lx and Ly too. And they can be a little complicated. There's cotangents in one of them. Anyway, so they can be a little bit more complicated. I didn't say too much about this. Recall the way we represent this. Again, this is all just a review right now. This little representation is actually way more important than you might realize at first. Okay, so recall that the total vector, which will be the length, is L, and the projection on the z-axis is, of course, bm. Again, to drive that home, I'll call that m sub z. One thing people also tend to forget is if they're, these drawings tend to put the cone in the positive z direction, but of course there's one in the negative z direction as well. So this is plus m sub z, there can be a minus. So there's your degeneracy. So anyway, yeah, there's just not much to say about this. Let's see. Okay, now let me get the big picture before we start reviewing. I'm actually going to review relatively quickly all of our Dirac, a lot of our operators for Smith, our Stern-Gerlach. I'm going to review them kind of quickly, just to remind you. And what do I want to say? Well, let's see here. So here we can see that the L squared operator on the wave function, based on this information right here, is h bar squared, gives it the right units, L times L plus 1. And again, that would be acting on a spherical harmonic. You can, so here you have the eigenvalue. And of course, you can assume that the L eigenvalue is the square root. It's the square root of that. This actually won't come up so much. The reason is that when you're doing vectors, and now remember I was saying we're going to be talking about adding angular momentum. It's a vector. And some of the things personally I tend to forget is that you want to do this, it's Lx plus Ly plus Lz, but you actually want to square it, right? So, r squared is x squared plus y squared plus z squared. What we're avoiding is the uncomfortable problem of a square root, of having an operator under a square root sign. So when we're doing all our vectors, our net vector will usually be the net angular momentum. We're going to want to know the square of the angular momentum, not necessarily the square root. Even though it's like, well, that's it though, that's the angular momentum. This is just not going to come up that much because to know the total, you have to work, again, with a vector representation. And recall that just like the radius of a vector, radius, when we've been dealing with radiuses since you were in middle school, is the square root of x squared plus y squared plus z squared, right? Well, what am I going to do if I have operators under a square root sign and I try to operate on a ket? I don't know, right? So that's a bloody mess. So we just basically don't do it, but we don't need to. Okay. Okay, so let's go back to, let me go back to this little drawing I just made a minute ago. One of the things that kind of slays me when I teach undergrads is that rotational energy. We always put rotational energy in physics as j squared. So again, you can see why the square of our angular momentum vectors is really the one that's important, because energy is going to be related to the square of the angular momentum. So it's angular momentum, just like p squared over 2m, we have j squared over 2i for rotation. I, of course, being the moment of inertia, which we won't really even talk about that ever again. So what's kind of funky is, and I try just to kind of ignore that it's happening when I'm talking to undergrads, is I'm using L instead of J. I'm using L instead of J when I'm talking about S and P orbitals. And they have learned in physics that I should be using the letter J. Well, why have I suddenly come up with a new letter for angular momentum when we already had one? Well, it turns out that because, all right, so you're in a chemistry class, this is quantum, it's all about electrons. There are subfields of theoretical chemistry where people worry about the wave functions of like the whole molecule, like the molecule moving. Like we have wave functions for electrons moving. What about the molecule itself? Very few theoreticians worry about wave functions of like the whole atom. Like that's important for like hydrogen, for like hydrogen tunneling. It's rarely done. Quantum in chemistry is only about electrons, aside from these very small group of people. Now electrons have, spin up, spin down, which is a form of angular momentum. And how often, think about our benzene molecule, how often do you need to worry about s orbitals? How much are all of your molecular orbitals composed of s orbitals? It's rare. Right? The p block has p orbitals, and the d block has d orbitals, and those have angular momentum. So the total, which is what the Hamiltonian is going to care about, is going to be this. So this is fundamentally why, at an undergrad level, we never use the letter J for angular momentum, because there's always S. It's absolutely unavoidable. They must be added. Now this is just straight up physics, vector addition, to give you this. And this is the only thing that actually matters to the Hamiltonian. And at a graduate level, you should know that this is the thing that will dictate what your molecular orbitals look like. That's why the double bond of a carbon atom, which again, I'm assuming you understand quite well from, you can just put it in your mind how the p orbitals add up and all that. That's why it doesn't matter diddly squat to the actual resonance structure, which is a molecular orbital of the Hamiltonian, because the Hamiltonian cares about J. And again, to be consistent with what I was saying before, really J squared, and now get this. Here's a little vector bomb for you. Huh? Is this right? You remember some of your, you forgot? Yeah, there you go. Now remember, as we get into, and I'm going to start right now, as we get into quantum mechanics, you don't know this and you don't know that, but you need to know that to add it together. Here, oh, and you also got a problem here. Oh, and S has the same issue as well. So you got a bit of a problem. Anyway, so there's a backdrop on why we're doing all this and a bit of a reminder. Okay, so when it comes to, we're going to start with the spin up, spin down. We're going to worry about introducing this part later. So tomorrow, today we're going to do S. And especially because we've already done quite a bit with S because of all our direct notation, our Stern-Gerlach, and all of these are the same thing. That spin up, spin down here is the same as why some electrons were up and down in the Stern-Gerlach, this and that. So a little bit of a reminder. And an introduction of some new operators that we're going to need. So we're going to have some new operators because when, I shouldn't have erased this, maybe don't worry about this so much, but what, no, I should write, let me write this as S. S is Sx plus Sy plus Sz, and the Sc is the thing, of course, is our basis set, right? That's, the Sc operator was what we used to create eigenstates. We created eigenstates for Sc, and we described Sx and Sy in terms of the eigenstates of Sc. So again, you understand all this stuff. What we're going to do is, we're calling that our basis set of plus or minus Sc. They don't work with Sx and Sy, right? They are not eigenstates of Sx and Sy, yet I need to know Sx and Sy. Here, let me square everything. I need to know Sx and Sy, or I got nothing. I can't generate the S squared vector to start to add to L and then to get the total to get the energy. So the trick is, we're going to remove these. So what we're going to do is we're going to introduce, of all things, ladder operators. So we're going to take what we've been doing, and again, in our SC basis set, we're going to get S squared, but we're going to do it in a way that we're going to eliminate Sx and Sy, because again, we don't have a choice about that. We don't know Sx and Sy. So we're going to change them out for ladder operators. Okay. Now recall that SZ on plus and minus, so plus and minus will be our basis set, is this, which is incredibly simple. And the representation, of course, is diagonal. So, and of course, SX are not diagonal. And again, that means that while my vector component in SC is defined with SY and SX is not, so how am I ever going to generate the total spin type of angular momentum, which then has to be added to L, which has the same issues, which only then can I get J, only then can I get my energy, and only then can I get my molecular orbital. So it seems like I have a problem that's probably unresolvable, regardless. And recall that that's also because of the uncertainty principle. Again, you know at this point that when you have an uncertainty principle, that's when you have a problem with your basis sets not working. You know, if they work for one operator, the operator that they were designed for, and then they won't work for the non-commuting operators. And you have to deal with that in some way. And for rotationalism, this is how you can deal with it, which is what I'm about to show you. The way you deal with that, and again, remember our goal is to get rid of the SX and SY because we have a problem, like I've been traveling on and on about the last 5 minutes.
Last line, it should be X on the SY, SZ should be SX.
Oh, yeah. In fact, it's in my notes, thanks, yeah. Right, it's positive, so it's got a ZXY, YX minus Z. Actually, we're backward on that one for some reason. 1ZX plus, right? So there's that. What was it? What was the thing that makes this one negative and this positive?
It's the HV.
It has another name. The permutation operator.
Like 1, 2, 3. What you're talking about?
Yeah. It has another name though. It's more common name. The cyclic permutation operator or something like that. Anyway, that's great. You remembered the name. I didn't remember the name. Okay. Anyway, so here we've got raising and lowering operators, and as you can see here that we can break them down to X and Y. So cool that, right? And based on what I just showed you, the representation is this. Look out for me, I may forget H bar. Here's S minus. Anyway, so yeah, look at that. That's cool. Notice they're off diagonal. That makes them non-Hermitian. Not that it matters that much. Okay. All right. So now the trick here. Let me go to another board. So I'm going to be writing out a whole bunch of. This is going to get messy. Kind of like when we did ladder operators. It's not going to be as bad, by the way, but just heads up. So S plus S minus, and of course the order matters here. So S. So if you want to just kind of roll with this, I mean, I think you're perfectly capable of foiling things out, but maybe if you want to just kind of nod your head and say, oh, okay, that's fine. Trust me, it's fine. This is from your book as well. Accurate, but hideously difficult to solve. Wait, sorry. Okay, so of course there has to be an I in it. So notice that you can guess what I'm about to do. I'm about to write a commutator. And that just happens to come about just, let's take this, multiply by that. So you get yourself a little I in there and get a commutator. And of course this is X. So you see how I'm about to get rid of SX and SY. And so that's going to be awesome. Let's see, then this is going to be I times the commutator, SY, SX. So that's why actually I put that, I was questioning why did I put that in that order, and now I remember. Because when it comes to our new friend here, let me remind you that this is minus I h bar s z. Right, just like right there. So I shouldn't have written that. Okay, so plus h bar s z. Okay. Okay, now here's a trick. Watch this. Okay, fx. Oh, squared. Yeah, terribly important because it needs to look like a vector. The correct way to add vectors, to add their squares. And everything's an operator. So what's kind of funny about that is, one of the reasons that this stuff is so painful is, especially if you get into things like the Dirac equation, is what happens when you need to take the square root of an operator. At that point you really are in a mathematical paradigm that really PhD physicists are the people you need to be talking to at that point, because you kind of blown the head off of a chemist. Okay, so here's the clever thing, watch this. I'm going to add sz squared, then I'm going to take it away. There we go. Of course, let's not forget just the dot product. Okay, so now what I can do is, now I'm pointing out that this is s squared minus sz squared plus h bar sz. And remind you that this is s plus s minus. Okay, now remember, s squared had an sx squared plus sy squared, plus sz squared, we're okay with sc squared. I had to get rid of the x, sx, and sy, and we have just done that. So s squared is s plus s minus, minus sc squared, plus h bar sc. Okay, so now what I've got is
plus SD minus h bar.
Huh?
Maybe plus SC plus SC squared plus minus h bar SD.
Well, hold on.
If you're trying to isolate it.
Oh, yeah. Is that right? Yeah, I gotta check my notes. That's where it would be, but yeah, let me check my notes. Yeah, I see. They'll just, thanks for pointing that out. I can tell my notes are in error. I just, 90% of the time I make an error, plus or minus. It's just I'm kind of doing things off the cuff. This time I'm looking at my notes because it's kind of complicated, and I realize my notes are wrong. I had that as minus and that as minus, so that's how I can tell that I simply got that one wrong. Thanks for pointing that out. It's obviously simple addition here. Okay, so again, cool. Ladder operators, drive. Just look at it. Hopefully you know that this takes SC plus and makes it SC minus. Just look at it, right? Hopefully you can do it in your mind. 1, 0 times this is 0, 1. And this one, 0, 1 down would become up. Or the other way. Did I do that right? 0, 1. Yeah, so I'm sorry, 0, 1, right? 0, 1 would become 1, 0. Yeah, it would, right? And that's S minus, so it'd be 1, 0 would become 0, 1, right? So these guys are cool with SZ. I have no problem figuring out what these guys do with SZ. SZ, I know what SZ does with SZ, and I'm able to get the total spin now. So in that, so see how clever that is? I can get the total magnitude of spin knowing just SZ, whereas in regular vectors as we've known them, there's an SX and an SY, and I don't know what those are, so I can't get the total spin. So what the only thing that bothers me about this is, how can both be true simultaneously? How can I have one representation for S squared that I have no way of knowing what it is, and I have another representation with the same operator, and this isn't a problem at all? The answer is that SX and XY actually work with each other in ways that are not intuitive, such that it is answerable, and this is the way you intuit it. Okay, now that we have S squared, let me show you what it's going to do, and I'm going to throw you a trick question that's going to blow your head off, even though it's unbelievably simple. Now that I have S squared, one thing as well, I probably should have put this on your homework, so I kind of feel bad about this. This is actually kind of difficult. So like if I told you make a matrix of S squared, so you put, plus, plus, minus, minus, plus, minus, minus, plus, right, and do all the operators, actually it's going to suck pretty bad. It can take you about an hour to actually wade through all of this multiple. So it's slightly complicated. When I was writing my notes, I had to do that. And I was kind of surprised that this is actually kind of a bit more difficult to write in matrix form. Now, anyway, so here's the matrix elements. And so, of course, in matrix form, it's what's important here is that, again, it's diagonal in the SZ basis. So when you see this, it's like, oh, okay, well, there's a matrix. I know about matrices. But remember, what you're really looking for is it diagonal? So I solved this in the SZ basis, and it's diagonal. So that means that these are the states. Let me say they're good with SZ, which they have to be because they are its eigenstate. So by definition they are, but they're good with S squared too. So, okay, now let me point out something. This is kind of funny. Remember that just like L squared, the L squared operator gives H bar squared L times L plus 1. Here. Let's operate on this. Here's our direct notation. And so this is. Okay, again, I just wrote the same thing, but now wait a minute. Does this add up? You see this? Okay, it's plus, all right, so H, let's forget the H bar squared, okay? 1/2 times 1/2 plus 1 is okay? All right, what about the minus half? What about spin SC down? Huh? Have I made a mistake? All right, so for the SC minus half. Huh? Seems like there's an error, isn't there? What would it be? Minus 1/4? Did I do that right? Minus a half plus 1 times minus a half? It's minus 1/4, right? So what did I do? They can't both be true. Huh? What did I do? What did I do wrong? Any takers? Okay, hold on a second. Again, it's a minus. So what's that?
H bar 0, 1.
Minus H bar over 2, right? Right? Okay, guys, this isn't S. This isn't SZ. It's S. Right? S. on a minus, plus or minus, is 1/2 h bar. Positive. The total spin is 1/2. SV on the minus state is minus 1/2. Now, this never got brought up before because we actually never ran into total spin. I actually did talk about total spin once, by the way. I don't know if you recall, but I pointed this out a long time ago. But the reason I didn't harp on that so much was because I'm talking about it now, and I had introduced this ladder operator. You hadn't even seen ladder operators. Anyway, it's just a little subtlety there that what you've got to understand now is that the plus minus state that you've known so well, you need to know that S is 1/2 h bar and SZ is plus or minus 1/2 h bar. But really you want it, again, let's not think about S but S squared, which again is 3/4 h bar squared. So again, I wanted to just point that out, but again, angular momentum by itself is rarely useful, but angular momentum squared. And it's not the same because it's S times S plus 1, right? I didn't square this. It's not 1/4, right? It's 3/4, just because of how funny quantum mechanics is. Okay, so with that, all right, now the point of this is that the Hamiltonian, for all the reasons I've been traveling on and on, is going to be sensitive to S squared, which is you're seeing is not behaving itself in a way you would like because we can't deal with Sx and Sy. And remember, next lecture is that I'm going to do all the same stuff for L, or when you have P and D orbitals, which is basically all the time. So now what I want to do is start adding these vectors, given the limitations I've just described. So what I'm going to do first is I'm going to do spins. I'm going to do 2 spins, like in maybe they'll be in S state, so we won't worry about L. So I'm going to add 2 spins. But now before I do that, I'm going to actually complicate it further. So this is the only part. Hopefully this hasn't been too mind-bending. This is the part where it does get a little confusing. Okay, so spin orbit coupling. And you know how I'm very concerned about inorganic chemistry. Is a constant times L dot S. Those are operators. Okay, now you may recall it's proportional to atomic number to the 4th power. So it gets, once you get past the 3rd row, it gets overwhelmingly strong. You can't ignore. So when you're on 1st, 2nd, 3rd row, you just ignore it. It's just not there. It's always there. You just ignore it. But when you get to the 4th row, which now kind of there's a lot of interest in 4th row, like rhodium, right? Iridium, or like catalysis. You absolutely cannot ignore it. It becomes the strongest part of the Hamiltonian. So you absolutely can't ignore it. Now let me remind you how spin orbit coupling works. One is, now this is only going to matter for P and D orbitals. And I'm not too worried about F orbitals. Okay, so what I've drawn here is a P orbital. Okay, and that's an angular momentum that's up. So that has 1 h bar of angular momentum. But the electron itself has spin that is, again, imagine it rotates on its axis like this. Versus this. Now I'll have the p orbital say this. Let's say that this is plus. This is like 2p1 plus 1. So I'm going to draw that the same way. But what I could have done is drawn the electron is spinning instead of clockwise, counterclockwise, or vice versa, whichever one it is. And due to spin orbit coupling, not the same energy. And they can be better. Again, my point is, once you get to high enough energies, these things may be vastly, vastly different by several eV, which is a huge amount. Now recall, one way to think about this is that these, the way that the electron spins about creates a magnetic field, because the spinning charges do that, and it's spinning. But it's also, it's behaving as though it's spinning on its axis, which is the magnetic field, and now the two magnetic fields. And I'm representing the magnetic field due to a p-type motion through its angular momentum. So two north-north, south-south versus north-south, south-north, right? So that should be lower energy, that should be higher energy. And whereas in undergrad level, hydrogen atom, we don't even talk about it, so those would be degenerate. Okay. Now, so one thing we're going to do is figure out how to deal with this. How to deal with this part of the Hamiltonian. So when it comes to the Hamiltonian and total angular momentum squared, I actually the reason I'm throwing this complication at you is that I've actually resolved most of the problem with those introduction of those ladder operators in terms of calculating total energy for total angular momentum, S or L. But this is something you throw in the Hamiltonian that will hideously complicate it further, and you really got to know about this. Okay, so let's see here. Let me remind you that we'll assume that we have spherical harmonic wave functions times spin wave functions. So this will be like so it'll be like a spherical harmonic and then another alpha beta, which again has no actual functional form. Remember when we talked about that? How spin wave functions are just alpha or beta? Weird stuff, right? Because we don't really know. That's sensible. How can we have an equation for something we don't really know what it is? I'm just writing this down again. Sorry, that's L. LZ. And LZ, by the way, now I think you know full well what SZ is, because that's our basis set for our Dirac notation for our Sturm-Gerlach this and that we spent just a tremendous amount of time on. LZ is actually, remember when you had to solve the 2D particle on a string Hamiltonian? That was LZ. So you've seen it before. Now, S squared, again, you're seeing this now for the first time. Often the S is capitalized to try to make sure that people don't confuse it with SZ, because you're so used to seeing SZ, especially in the representation of electrons as spin up and spin down. So sometimes it's capitalized to make sure that you're not getting that confused. And of course, you can see that the ket is a simultaneous, remember this from the book, it's a simultaneous eigenket of multiple operators. So again, just to make sure you're not off the wall here, if you're looking at that thing, wait, don't I already know that? Didn't we cover that? Yeah, we did. Just want to make sure we're all on the same page. Okay, now again, when it comes to understanding heavy elements, I'm going to have J squared in the Hamiltonian total angular momentum. That's going to be a cakewalk. It's not too bad. But I'm also going to want to throw in L dot S into the Hamiltonian. And the purpose here is to correctly add up all of this, angular momentum in such that we get eigenstates of the Hamiltonian, because that's the only thing that matters. Okay. So this is, again, the only part that's going to get complicated is this. SZ, spin orbit, and of course I'm asking whether I can know, what can I know if not at the same time. I also like covering this because it shows you how to deal with these vectors. When an operator has a vector form, how do you deal with it? Right, so I look at SZ times this And I'm like, well, what does that really look like? And you can see that it's just the individual components. You know, I use a dot product, but really it just means that x times x plus y times y plus z times z. So it's relatively simple. Because when I look at this, I'm actually not necessarily sure what I should do with that, right? I mean, I think I get a dot product, but then I see that, and I'm like, okay, well, I can deal with that. Okay, so now, of course, the z part will get wiped out. And then we're going to have sz and sy. The L part doesn't span the same space technically, so it can just be, it can be not considered. So we're going to have an sc and an sx, which is going to be an I h bar sy. But let's not forget the okay, so that's gone. Oh yeah. Okay. So SC and SX is IH or SY. Okay. I got a little confused there. Sorry about that. So again, I hope you can see why I'm doing this. Because SC and SY, LY is just not important because it doesn't span the same space. So SC, SY is in SX. Sorry, let me, I can see I'm just about out of time, so I'll just finish up with this. Okay, so the point of this is that you do not get 0. Okay, likewise, LZ. And I won't bother to go through it all because of lack of time. Again, hopefully this is not too hard to even do it in your head to see that this is the case. Let's see here. Last bit, let me just state that if J is L plus S, therefore the Z operator with the spin orbit is equal to 0 and J squared with the spin orbit operator is likewise equal to 0. And therefore, so this net sum is that to know what the spin orbit Hamiltonian is going to do, you need to know its states. But knowing L, LZ, S, SZ is no. Right? So the problem here is that, again, I've shown you that if you know that an orbital is a PZ, so that's 1 and that's 0, right? If you know that an electron is in the PZ orbital, you know that this is 1 and that's 0, and it's spin up. So that's 1/2 h bar and that's 1/2 h bar. Oh, well, I should square them. Sorry. Okay, so in other words, again, if you know this, right, so these are 2p, so p plus 1, p 0, p minus 1. So I understand this very well. That's a PZ orbital. So I'm telling you, I got a PZ orbital. What's the spin orbit coupling? Well, again, I know what a p, I know L times L plus 1. This is 0 because it's a p0 orbital. I know it's spin up, so that's 3/4 h bar squared. That's plus 1/2 h bar. So I know all this. But do I know the spin orbit coupling? No. No. You don't know this. This sucks. Because now what do you do with this? Because this is, I mean, I understand this, but I don't know what else to do with it. Yet this is useless. Now you see the nature of the problem, right? Again, spin orbit coupling is really important. So the answer is that you're going to figure out J squared, which is L plus S squared, which is going to be L squared plus S squared. And you're also going to figure out JZ. So again, here's the idea. You're going to take this information. You're going to take this information and you're going to transform it into J squared, JZ, and you're going to have a total spin. You're going to have a total spin. The total spin and total angular momentum. You're going to have to transform between knowing these things from our electron orbital stuff that we learned in high school. You're going to have to do this and transform it into a representation of net angular momentum and its z component, L and S, which you still do know that still. So some of this is retained. And when you have it in this form, then you can know the spin orbit energy. That's the idea. So next class, I'm going to show you how to go from knowing this to knowing this. That's the purpose of the next lecture. All right, I held you over. This is one of the worst days.